Here's our last example about work. A spherical tank of radius 3 feet is full of water. Find the work required to pump the water out of a spout that extends 2 feet beyond the top of the tank. What I want you to do is imagine looking at this tank from the side. From the side, our tank is a circle, okay? And then it has a spout that sticks out of the top. In order to help this make sense mathematically, imagine that this circle is centered at the origin. So this is the y-axis and this is the x-axis. Okay, we know that the tank has a radius of 3. So this is -3 and this is y value +3. And we know that the spout extends 2 feet. I just realized that that says feet. A spout extends 2 feet beyond the top of the tank, so this y value up here where the top of the spout is y value 5. Now, this circle we can write as x squared plus y squared equals radius squared. The radius is 3, so we have 9 on the right side. Now, this tank is full of water, this entire circle. Okay. What we're going to imagine to do in any of these problems that involves pumping water out of some sort of strangely shaped tank, we're going to imagine taking the water and slicing it into skinny little slices. Okay. Each of these slices has thickness delta y, and I imagine the height of each slice as a variable y. Remember, the slices range all the way from -3 to +3. Okay, and then what we're going to do, similarly to the previous example where we were lifting some kind of rope, we're going to figure out the situation for what happens for one slice, and then we're just going to add all those slices together, let the number of slices go to infinity, and recognize it as a definite integral. So we know the volume for one slice is the cross-sectional area, which is pi times r sub I squared, times the thickness of the slice, which is delta y. So I'm taking this curve and solving for x in terms of y. So x is the square root of 9 minus y squared. That gives me the right half of this circle. The r sub I is the same as x sub I. So it's the square root of 9 minus y sub I squared. So the volume of each slice is pi times 9 minus y sub I squared delta y. Okay, now we're working on getting an expression for the work to move this slice of water up to the top of the pump. So what I need is the force, or the weight. Those are really two words for basically the same thing. Okay. The weight is the volume of water times the weight density of water, which is 62.5 pounds per foot cubed. So we have 62.5 pi times 9 minus y sub I squared times delta y. We also need to know the distance that that slice of water needs to move. That water needs to move from its current y value up to the top of the pump, which is at 5. So the distance is 5 minus y sub I. Now the work is the force, or the weight, times the distance. So I'm going to take these two expressions and multiply them together. Okay, now that's the work required to move one slice of water out of the tank. For all the slices, we just add up all those individual pieces. And then, to get the best expression, we take the limit as n goes to infinity. We recognize that as the limit of a Riemann sum, so we have the integral from negative 3 to 3. So 62.5 pi times 9 minus y squared. Oops. To evaluate this integral, you can pull the 62.5 pi out front, FOIL these two binomials together to find your antiderivative. Okay, there's some work here that I'm skipping, but we get 18,000 pi, and because it's work, our unit is foot-pounds.